In Neural Networks 1, we looked at the core mechanics of neural networks and how to build them from scratch. Specifically, we looked at how they learn through the cycle of forward pass, backpropagation, and gradient descent, and how at their core, neural networks learn transformations which map inputs to outputs. Beyond those core mechanics, there are a lot of surrounding details when it comes to training these networks, and in this module, we're going to cover a wide array of them. We'll also get an idea of what's deep about deep learning. We'll then finish with a demo where we'll apply this knowledge, this time with a framework. Here's the long list of things we're going to look at. There's a bucket of items here because deep learning is largely an experiment-driven, empirical endeavor. Often, something is found to work, and then some kind of explanation comes afterwards. And so this is a list of things which have been found over the years to enhance neural network training and performance, and they continue to change. There's no real way around this but straight through. The important thing right now isn't to memorize, but gain an intuition of what these things are and why they matter. You'll almost certainly be coming back and refreshing on this stuff as you experiment. The good news is all of these are implemented in multiple frameworks, and you'll see a bunch of links in the demo. The first thing we'll talk about is gradient descent. In the last module, we covered sending a number of examples through the network during the forward pass, calculating an average loss, and then adjusting the weights accordingly. When we send our entire dataset through the network each time before calculating a loss, it's called batch gradient descent, and it's the simplest approach. But there are a couple of issues with this approach. First, it can take longer to get feedback on performance because the network has to process our entire dataset on each forward pass. And what if our dataset can't fit into working memory? To deal with this, we can use stochastic gradient descent, or SGD, instead. Rather than sending the entire dataset through the network on each forward pass, we'll process a single random entry. Because the network has much less to process on each forward pass, this will lead to much faster feedback and the ability to process datasets which can't fit into memory. Rather, the data can be streamed in from storage. But this comes at another cost in that SGD has an erratic convergence path towards a minimum. Imagine we have a network with two weights to train, W1 and W2, and we're looking at the loss surface from the top down like this, so the minimum is at the center. With batch gradient descent, because we're taking the loss across the whole dataset, the convergence towards the minimum tends to be smooth. On the other hand, SGD tends to have loss values which jump around. The loss does reduce over time, but the path towards the minimum tends to be erratic, and as it gets closer to the minimum, it tends to hop around rather than converge. Rather than picking one extreme or another, an effective popular compromise is to use mini-batch SGD where, for each forward pass, a random subset is sampled from the dataset and sent through the network. So in this case, we're not sending the entire batch, and we're not sending just one example, but a subset. This provides benefits from both sides. Batch operations can benefit from hardware matrix operations, and the convergence is less erratic, though still not as smooth as regular batch gradient descent. It still zigzags down the hill, but in practice, it works well enough to make the trade-off worth it. Now, in practice, the dataset isn't sampled each time for the forward pass. Rather, it's shuffled at the beginning, then divided into batches up front. The first batch is then sent through the network, the weights are updated, then the next batch goes through, and so on until the entire dataset is processed. One full run through the dataset is called an epoch, and this is what we did in the demo in Neural Networks 1. In terms of batch size, it varies depending on the dataset. It typically ranges between 32 to 512, with 32 being a popular starting point for modest datasets, and it can get larger from there depending on the dataset size and hardware available. Let's talk about learning rates. As you may recall, after we compute the gradient, we update the weights by subtracting the gradient from the current weights. We also multiply the gradient by a learning rate to control the size of the weight change, and this learning rate needs to be sensible. If the learning rate is too low, the loss might decrease so slowly that it takes an unreasonable amount of time or doesn't reach the minimum at all after some computation limit. On the other hand, if it's too high, the loss may keep overshooting the minimum, bounce around, and actually increase over time. So the learning rate needs to balance speed of convergence against risk of missing the minimum. One way to accomplish this is to try a bunch of different learning rates, and rather than trying them manually, we can use some hyperparameter search technique like we did in part 1. There we used grid search for our naive Bayes text classifier, which simply tried a fixed set of values and let us know which one worked the best. This is straightforward and intuitive, but if we have a large set of hyperparameters to search over, grid search can be time-consuming and inefficient. Another technique, probably the most popular one, is random search. Here, a search space is defined by setting lower and upper bounds and randomly sampling points in this space. And this often leads to discovering great hyperparameter combinations that would have been hard to find intuitively or using some fixed set of values. At first glance, it may be hard to believe that random search would even work, but it's been empirically shown that it can perform just as well as grid search given a certain number of trials. So in general, I'd favor random search unless I already have a good idea of decent hyperparameter values to try. Both random search and grid search can be parallelized. Bayesian optimization is a different approach. In contrast to grid and random search, Bayesian optimization looks at the result of past trials and tries to predict which regions of the search space will give better results. And because of that, it may find better hyperparameter values in less time and could be preferred when training time is short and function evaluation is expensive. There's a link on the module page for more information. There are other approaches such as genetic algorithms, but most of the time, random search will work just fine. So those are a few ways to find effective learning rates, with a popular default being 0.1 or 0.01. An alternative to using a fixed learning rate is to use a learning schedule, where we start with some learning rate and then reduce it over iterations. The idea is to move towards the minimum loss fast at the beginning, and then slow down to reduce the chances of missing or bouncing around the minimum. One approach is exponential decay, where an exponential decay function is applied to the learning rate at each iteration. Here, d is the decay factor, which is some hyperparameter, and t is the iteration. Alpha continues to also be a hyperparameter. There's piecewise constant decay, which is simply using a constant learning rate for a set of epochs, then reducing it for the following set of epochs, and so on. It's simple, but requires finding a decent number for the set of epochs to define the interval. An interesting one is one-cycle policy, which starts by increasing the learning rate for a certain number of iterations until some maximum, then reducing it to some minimum lower than the original starting rate, and it's been shown to help networks reach higher accuracy in less time than other techniques. There are other learning schedules, such as error-based decay, where the learning rate is reduced only when the error rate stops dropping. Okay, we've covered mini-batch SGD, ways to search for good learning rates, and using learning schedules to help us converge to a minimum faster while reducing the risk of overshooting or bouncing around it. Up to this point, the loss surfaces we've looked at have been convex. That is, there is a single minimum, so the training algorithm should get to the minimum as long as we use a reasonable learning rate. But most of the time with deep learning, it won't be so simple. As networks become deeper, the loss landscape changes to include hills, ridges, and bumps leading to multiple minima. The lowest minimum is known as the global minimum, while the rest are local minima. And in these situations, there's a chance the algorithm converges to a local minimum rather than the global minimum. This can happen if our learning algorithm, initialized with random weights, starts on a part of the surface which leads to a local minimum and settles there, as we see in this illustration. This is the loss landscape of an old image classification network called VGG56. It's highly complex with plateaus, ravines, and small hills. The gradient can change dramatically between iterations, and there's plenty of opportunity to get stuck somewhere and never reach the global minimum. There are multiple ways to avoid this. SGD itself can help through its erratic convergence. Just by chance, if the algorithm is near a local minimum, the next iteration of SGD may jerk it out in such a way that the algorithm continues converging to a lower minimum. You can see this sometimes when you're training a network. The rate of loss minimization will start slowing down, and then suddenly it'll accelerate again. A learning schedule which starts with a relatively high initial learning rate can help as well. Random starts elsewhere in the initialization space can also lead to converging to a lower minimum. A more sophisticated approach is to modify gradient descent itself. Plain gradient descent looks at only the current gradient and doesn't care about past gradients. Now, think about a roller coaster making its very first drop. As it rolls down, it gains velocity and momentum, and this momentum helps the roller coaster get past the next hill, a flat section, or through a loop. This concept of momentum can be added to gradient descent by having the formula take past gradients into account. Here we're introducing a moment factor m, which includes a friction coefficient beta set between 0 and 1 inclusive, but typically set to 0.9, with the initial momentum factor set to 0. When the friction coefficient is set to 0, we get plain gradient descent, but as we increase it, we introduce some gradient memory, and the higher the number, the greater the momentum. The next weight adjustment then is the current weight plus this momentum factor. And we can call these functions which modify weights and biases optimizers. To illustrate the difference momentum can make, this was our plain gradient descent example from the previous module where it took a number of iterations before getting close to the minimum. If we roll back the descent, we see the loss is at 22 after 4 steps with plain gradient descent. Let's compare that against gradient descent with momentum. So here we're using the same starting weight value of 0.5, which leads to a loss of 72.25. That loss is plotted as a blue circle on the curve. This time we've incorporated momentum into the gradient descent step. Because the initial momentum is 0, the next weight to try is the same as plain gradient descent, which is 1.01. That leads to a loss of 48.58. So the first 2 weights tried led to the same loss as plain gradient descent, and we're no further ahead. The next weight to try at step 3, however, is larger. In plain gradient descent, it was 1.43. With momentum, it's 1.89, so we're taking bigger steps with momentum. The loss at the third step then is 18.82, and the loss is now lower after 3 steps with momentum than it was after 4 steps with plain gradient descent, so we're already ahead, so to speak. And finally, at the 4th step, we're already close to the minimum. Alright, so with momentum, the loss is close to the minimum in a fraction of the steps it took with plain gradient descent. That's nice, but there's a trade-off here in that momentum may make the optimizer overshoot the minimum a few times, but overall, using momentum with a reasonable friction coefficient still leads to greater benefits than using plain gradient descent. Now, aside from faster convergence, we can imagine how the momentum optimizer, with the memory of past gradients, can help a learning algorithm progress along flat sections and over small hills. In addition, it can also dampen oscillations. Imagine having a loss landscape that looks like a taco shell, so steep canyons on either side, but with a very gentle slope in the middle towards the minimum. A vanilla optimizer would spend a lot of time traversing up and down the sides. It would go up one side, course correct by turning around, then go up the other side, each time making only small progress towards the minimum. Momentum, however, averages out the gradients in all directions, so with a coefficient of 0.9, momentum would be averaging out the last 10 gradients, pushing the gradients along the sides to 0 while maintaining an acceleration in the middle. But another way to deal with oscillations is to dampen the larger ones for a given weight. This leads to another optimizer called RMSProp, which stands for root mean square propagation. Here, the optimizer aims to scale down the gradient for individual weights based on past gradients. This is the formula for the scaling factor where S is a vector. The gradient at each step is squared element-wise, which means the value that's added to the running sum is always positive. In addition, there's a decay rate beta, which ensures recent gradients will be weighted more, while older gradients are discounted. To calculate the new weights, the current gradient is divided element-wise by the root of the scaling factor, plus some smoothing value epsilon to avoid division by 0. Epsilon is usually set to a tiny number. The end effect is that this decays the learning rate faster for steeper slopes and slower for gentler slopes, resulting in a dampening effect. An additional bonus is because this optimizer is adaptive, it's less important to come up with a good learning rate. We can start with a reasonable default rate and let the algorithm take care of the rest. And finally, we'll look at ADAM, which stands for Adaptive Moment Estimation. With RMSProp, the optimizer keeps a list of squared gradients only, which means directional information is lost. With ADAM, the optimizer keeps a moving average of both the original gradients and squared gradients. Both moving averages have a decay rate with beta 1 for momentum typically set to 0.9 and beta 2 for the squared gradients typically set to 0.999. The weight update step is then m over the root of s plus an epsilon term, so essentially we're taking an average of an average. And these aren't the only optimizers available. There are others, such as Nesterov accelerated gradient, which is a modification on the standard momentum technique. It measures the gradient slightly ahead in the direction of momentum rather than at the current position. NADAM is Nesterov combined with ADAM, and there's ADAMAX, which modifies the scaling factor in ADAM. So, which one should you pick? As is often the case with neural networks, there's no clear answer. A good rule of thumb is to start with either RMSProp or Adam and see how they perform. Most of the time, one of them is going to work. If not, then try NHE or an Adam. I've included links to learn more about these optimizers. The good news is that local minima in complex loss surfaces are rarely a problem, so we don't have to get to the global minimum to have an effective model. If our optimizer gets us to a decent local minimum, that's often good enough. Let's move on to activation functions. These three here, sigmoid, tanh, and relu, are the most popular ones. Let's go through them one by one. With the sigmoid function, an input results in an output that's bound between 0 and 1. As we can see in the graph, the output of sigmoid approaches 0 as the input becomes smaller and approaches 1 as the input becomes larger. This maps well to modeling a probability, as we would with binary classification. It offers a smooth continuous derivative, which is ideal for gradient descent, and the inputs are zero-centered for a simple decision boundary between, for example, true or false. So, assuming the threshold for classifying something as true is 50% or 0.5, then any input above 0 will map to true, and any input below 0 will map to false. But there are a few drawbacks. First, as the input magnitudes get larger, the curve gets flatter on either end. This results in gradients close to 0 because very little change is happening on those extreme ends. When gradients calculated around those points propagate back through the network, the gradients at each earlier layer subsequently get smaller and smaller until the weights in the earlier layers of the network stop updating. That's because the weight update steps there are essentially subtracting 0. This is the vanishing gradient problem, and there are a variety of techniques to mitigate this, which we'll see. The other issue is that outputs are centered around 0.5. Convergence is often faster if the average of input variables from one layer to the next is close to 0. That's not the case here. Sigmoid activation functions can potentially lead to slower convergence because there's a positive bias. Lastly, exponentiation makes the sigmoid a bit more expensive than the other activation functions, which don't use it. The tanh function partly addresses the shortcomings of the sigmoid function. Like the sigmoid, tanh squashes its input between an upper and lower bound, but in this case from 1 to -1. So its outputs are zero-centered. This allows the output of each neuron to have a better chance of having a mean of 0, though that's not guaranteed. However, tanh still suffers from gradient saturation on either end, and exponentiation still makes it more expensive than the alternatives. Lastly, there's rectified linear unit, or relu, which, along with its variants, is the most popular activation function for hidden layers today and is often the default choice. We used the relu when we built a neural network from scratch in the last module, and as you may recall, the function itself is simple and computationally cheap. Take the max of either 0 or the input. That's it. It's also been shown empirically to converge faster, probably due to the gradient being simple and non-saturating past 0. The gradient is always either 0 or 1. This also enabled the training of deeper networks when the activation function was introduced. But poor weight initialization and a high learning rate can lead to dying relus. This is where a unit outputs only 0. This can happen when the weighted sum, so input times weights, becomes negative for all training instances. Because the gradient then becomes 0, the weights no longer update, the unit stops learning. To address the dying relu problem, we can try a few variants. Leaky relu allows a small gradient for negative inputs. The slope for negative inputs is controlled by a hyperparameter alpha and set to some small value, typically 0.01. This avoids dying relus, though a unit may update very slowly for a while before waking up again, so to speak. Leaky relu has been shown to perform better than regular relu. There's also parametric relu, where alpha itself becomes a learnable parameter, and LU, exponential linear unit, where for negative values, the activation becomes sigmoid-like. We get a smooth gradient for negative inputs, with alpha dictating at what point the gradient approaches 0. The downside is there's still a potential vanishing gradient problem for large negative numbers, and it's slower to compute due to the exponentiation. In terms of what to pick, for any units in hidden layers, especially for fully connected layers, go with relu or some variant like leaky relu. And for an output layer, if it's for regression, then we don't need an activation function. If it's for binary classification, go with sigmoid. And if it's for multi-class classification, go with softmax, which we learned about in the last module. Alright, weight initialization. Up to this point, we've assumed weights were initialized to small random values. In the demo from the last module, we initialized weights to be between -0.5 and 0.5, and it worked alright for our purposes. One thing to get out of the way is why don't we initialize all the weights to the same value, say 1? If we do that, the signals which get propagated will be the same, and all units will update in the same way. But the power of neural networks comes from associating different weights with different units. So by starting with random weights, this symmetry is broken. But can we do better? After all, if neural network training is about gradually changing the weights until we arrive at an acceptable loss, then maybe how the weights are initialized can contribute to this goal. One refinement is called Xavier or Glorot initialization. Here, the idea is to initialize each weight from a distribution with mean 0 and a variance based on the fan-in and fan-out of the weight. Fan-in is the number of incoming connections, and fan-out is the number of outgoing connections. And the theory behind this is to try keeping variance the same across every layer and scale the range of the weights based on the number of connections. The more connections, the smaller the weights. Keeping this bound helps to avoid large magnitude sums, which could lead to vanishing or exploding gradients. Here we see both uniform and normal distribution variance. The normal distribution has a standard deviation equal to the root of 2 over fan-in plus fan-out. Xavier initialization is usually reserved for sigmoid or tanh units. Another technique is He initialization, which also has uniform and normal distribution variance. Here the scaling factor is based on only the number of fan-in connections, but otherwise the idea is the same. He initialization has been shown to work well for relu units and is a fine default. Alright, feature scaling. Let's say we want to build a network to predict car prices, and two of our features are car age and kilometers driven. Car age will likely be in the range of double-digit numbers. Kilometers, on the other hand, could range from 0 to the hundreds of thousands. These two features are drawn from different scales, magnitudes apart, and this can be a problem. With a neural network, large input values can result in slower convergence, so when we have inputs with wildly different ranges, it's advantageous, though not necessary, to scale them down to the same range. And two common techniques are normalization and standardization. Normalization, also known as min-max scaling, scales values so that they fall in a range between 0 and 1, or sometimes between -1 and 1. This is done by subtracting each value by the minimum value in the range, and dividing it by the max minus the min. The other approach is standardization, which scales the values so that they fall within a range with mean 0 and a standard deviation of 1. Scaling a value entails subtracting the mean and dividing it by the standard deviation. Okay, so that's normalization and standardization. And the point of either is to reduce the amount that weights need to shift to accommodate varying examples. And because our loss landscape is now closer to symmetric, we can then use a higher learning rate. But which one to use? For neural networks, as a rule of thumb, prefer normalization unless the feature has a distribution close to standard normal, basically the distribution resembles a bell curve, or there are important outliers. This is because, in normalization, outliers will squeeze the other values into a much smaller range. An important thing to keep in mind is to use the transformations from training data only. So at training time, normalize the training data set and save the scaling values. Then at test time, use the same scaling values for the test data and for subsequent predictions. This is because we don't want our scaling to be influenced by test data and therefore get some kind of bias. Okay, so far we talked about reducing the chances of vanishing or exploding gradients through using certain activation functions and weight initialization techniques. We also talked about normalizing or standardizing our features to help with training stability. But despite all that, once we pass the first layer, output distributions can still change within the network and still potentially lead to instability. This is where a technique called batch normalization can help. Batch normalization standardizes the outputs of each layer, either before or after the activation function. So it's called batch normalization, but really what happens is standardization. The general effect is faster and more stable training, higher accuracy, and allowing for higher learning rates, and we'll get to why in a moment. It's called batch normalization because a layer's output is standardized using the whole batch's mean and variance. Let's clarify with some math. To perform batch normalization on a layer, we first calculate the mean layer outputs of a batch. So if our batch size is 32, let's say, 32 layer outputs will be summed batch-wise and the average taken element-wise. So in this illustration, the layer is going to output 32 vectors. Those vectors will be summed, and each element in that vector will be divided by 32. We would then end up with a vector of means. The next step is to calculate the output standard deviations across the batch to end up with a vector of output standard deviations. In this example, the first layer output would be subtracted by the mean of the layer outputs, then squared. The second layer output would be subtracted by the mean, then squared. All these would be summed, then divided by our batch size, 32. Now that we have means and standard deviations, we can calculate the standardized outputs. That's each layer output subtracted by its respective mean, then divided by the root of its respective standard deviation plus some epsilon value. The epsilon in the denominator there is to avoid division by zero scenarios. At this point, the standardized outputs would have a mean of 0 and a variance of 1. Okay, so far this is hopefully straightforward. We're doing the same thing here as we did in feature scaling, except with a batch of data. But to create the layer's final output, there's an additional scaling and shifting step. The standardized outputs are element-wise multiplied by another vector, gamma, that scales the variance, and another vector, beta, is then added to the result to shift the mean. Gamma and beta are learnable parameters trained during backpropagation to minimize the loss. Okay, so what's happening here is that we're taking a batch of layer outputs and using the means and standard deviations from that batch to standardize each output such that it has a mean of 0 and variance 1. We then have the network learn parameters to best scale the variance and shift the mean. You might be thinking, what's the point of that? Why standardize the output just to scale and shift it again? Why does this work? Well, the explanation for why batch normalization works has changed multiple times since its first introduction. The original explanation was that it reduces something called internal covariate shift, but that was debunked when noise was injected into the data and batch normalization still outperformed. The prevailing theory today is this: batch normalization smoothens the loss landscape. That is, when the loss landscape has a lot of rapid changes, there's a high variation in the gradient. This leads to uncertainty in training and having to use slower learning rates. In contrast, batch normalization smoothens the loss landscape such that the variation between gradients is smaller and more orderly while still maintaining the original minima. This in turn is friendlier to high learning rates, leading to faster convergence. Gamma and beta are there to let the network learn how to best scale and shift the distribution as it sees fit to minimize the loss, and is even free to scale and shift in such a way to undo batch normalization if that's what leads to better results. As far as I know, there isn't a clear theoretical explanation for why batch normalization works, which is one of its downsides. Other downsides include it being expensive and sensitive to batch sizes. As of this recording, research labs such as DeepMind have created normalizer-free image recognition models which have achieved high accuracy while being faster to train. Later in the course, when we learn about transformers, we'll look at a variant called layer normalization, which is more common in NLP. If we use batch normalization, do we still need to normalize or standardize our inputs? It probably doesn't hurt. As an alternative, we can add a batch normalization step in our input layer, but it's an experiment to be done. Recall when we talked about feature scaling, we mentioned that we need to use the same scales from test time at inference time. It's the same here. Gamma and beta are learned with backpropagation during training, and those values will then be saved and used during inference. The mean and standard deviations are estimated using an exponential moving average during training. These estimates are then used during inference. Okay, moving on. In the Building Models module, we covered a concept called overfitting and a few ways to mitigate it, including choosing simpler models, trimming features, and getting more data. Another approach was regularization. Regularization, as you may recall, is any technique that forces a learning algorithm to generate a less complex model, which hopefully prevents overfitting. Let's look at a few now. A simple and intuitive technique is early stopping. When training a model, if everything is going to plan, the validation loss should follow the training loss. At some point in most everyday neural network models, the training loss and validation loss will start diverging, indicating the model is starting to overfit. Early stopping is simply taking the version of the model at the point just before the validation loss and training loss diverge. Modern frameworks make this simple by saving a snapshot of the model after each epoch. Keep in mind that in modern deep learning, a little bit of overfitting has been shown to be okay. Another technique to fight overfitting is by regularizing the weights. In the Building Models module, we had this example where a model was so overfit that a regression line perfectly ran through all the training samples. The consequence of this is that during inference, any prediction for an unseen example is probably going to be way off. Visually here, we see a wide distribution of weights for the model. And if we could force the model to pick a narrower distribution of smaller weights, it wouldn't be so accurate in training, but it would certainly be more generalized. And that's what L2 regularization does. So given some loss function L, an additional cost is tacked on at the end in this form. Here we're summing the squares of all weights and taking a proportion of that value. That proportion is controlled there by lambda, known as a regularization parameter. The higher the lambda, the stronger the pressure, so to speak, to learn smaller weights, since the loss is going to be higher. Specifically, larger weights are penalized. Note that weight regularization techniques such as L2 are used only during training and not during inference time. Another form is L1 regularization, which follows a similar principle except the added cost is just the sum of the weights, not the sum of the squared weights. This induces a constant shrinkage across the weights, so even weights already close to zero will get pushed down. L1 then is said to encourage a sparse model with few non-zero weights. Practically, it leads to the less important features getting a weight of 0, and so it can also be viewed as a feature selection technique. So those are two weight regularization approaches, and they're often used with smaller models. But the large models that we'll leverage when we start learning about transformers have so many parameters going from the hundreds of millions and into the billions and soon the trillions that weight regularization doesn't have much of an effect, as far as I know. For these situations, a popular regularization technique that scales well is dropout, and it's conceptually straightforward. With dropout, each unit in a layer has some probability p of being dropped at every batch. Effectively, they get disconnected from the network. So with p equals 0.5, half the units in each layer on average should drop out. In one batch, the network may look like this, and in the next batch, the network may look like this. So why would this work? The intuition is this reduces the chance of a model learning patterns which are coincidence and useless, and developing units with highly correlated behavior. It forces the model to make do with fewer and smaller values, which forces it to generalize better. And because at each batch we're essentially training a different neural network, the final model can be seen as averaging over many neural network architectures. This mimics a technique called ensembling, which entails training multiple diverse models to make a prediction. Dropout, however, is computationally much cheaper. In practice, the dropout probability p is set anywhere from 20% to 50% depending on the model, and it doesn't have to be applied to every layer. Dropout isn't used at test or inference time, which means units will be receiving much larger signals. To account for this, a layer's outputs are scaled down in proportion to the dropout rate. This is done by either multiplying the output by 1 minus p or dividing the output during training time by 1 minus p. So weight decay and dropout are both techniques which add some noise to the network. And in the same vein, so does batch normalization. And that's why in addition to allowing for larger learning rates and more stable training, it also provides a regularizing effect, the source of the noise in this case being the standard deviation and mean of a batch. So that concludes a fast tour of neural network training details. Again, don't worry about memorizing any of this stuff because we'll be using a few of these techniques in the demos and only a handful are applicable to modern deep learning for NLP. We're going to come back and talk about sensible defaults, but let's go through a quick demo first. Okay, so here I've reopened the NLP Demystified Neural Network Foundations Colab notebook. You'll find a link to this notebook on the module page. You can also get to it through the NLP Demystified GitHub repo. Once you have it open, scroll down to the Neural Networks 2 section. As usual, we'll upgrade spaCy and install this small English statistical model. I've already done this, so if you haven't, please pause the video and do so now. For this demo, we're going to again use the 20 news groups dataset. This is so that we can compare how a neural network solution performs against our naive Bayes classifier from part 1. It's also a challenging dataset provided we remove all the metadata, which we do here. I promise this is the last time we'll use this dataset. To build our model, we're going to use TensorFlow Keras. Now, Keras does come with a tokenizer, but it's basic. So for now, we're going to stick with spaCy for pre-processing because it has a bunch of specialist linguistic features. To that end, we'll load the statistical model. We'll also disable named entity recognition and parsing since we won't use them here. As we've done before, we'll set up a tokenizing function. Here we're going to take the lowercase lemma, remove any token that's less than 2 characters long, and also remove punctuation, stop words, spaces, and any non-alphabetic tokens. Next, we'll set up a simple utility function that takes some text, tokenizes it, and then rejoins it with a pipe character. The reason why we're doing this will become clearer in a moment. We'll pre-process the training corpus at this point. In the demo on topic modeling, we used NLP.pipe to pre-process batches of sentences using multiple processes. And you can take a look at that demo to see how to do that. In this demo, we'll just keep things simple and pre-process sequentially. This will take a few minutes, so I'll fast forward through this section. Okay, so once that's done, we should have pre-processed strings where each token is delimited by a pipe character. Next, we'll split the data into train validation sets. Here we're splitting it 85% train, 15% validation. I've also set random state to 1 so that we can get the same split each time. And these are the lengths of our train and validation data sets. We'll bring in Keras at this point. Keras is a deep learning framework built on top of TensorFlow. In simple terms, you can think of TensorFlow as an ecosystem and platform for machine learning, while Keras provides a friendly way to compose models and iterate fast. There's PyTorch as well, which is more frequently used in research. They're both great, have similar features, and you can't go wrong with choosing either. And if you know TensorFlow Keras, it's easy to pick up PyTorch. We're going to use the Keras tokenizer to simply split our training strings into tokens. The reason why we're doing this is so that Keras can build an internal vocabulary to help us vectorize our data. There are other ways to go about this, but this was the most straightforward. So we'll instantiate a Keras tokenizer here and specify no filters, no need to lowercase since that's already done. We'll split on the pipe character, and we'll also specify an out-of-vocabulary or OOV token. Remember that our vocabulary is based on training data only. When our model's deployed, it may encounter tokens it hasn't seen before. In that case, those tokens will be marked as this OOV token. Before we can tokenize, we'll need to fit our tokenizer on the text. That is, have our tokenizer go over the training data and generate a vocabulary much like we did with scikit-learn's count vectorizer from part 1. Because we're just splitting, this will go by quickly, so the reason we use the pipe character was to preserve Spacey's tokens. Of course, make sure the pipe character is safe to use in your own datasets for splitting. We can look at what the tokenizer holds internally through its getConfig method. So here we can see it processed around 9,600 documents, and there are various indices for the vocabulary such as index to word to index, and word counts. Our OOV token takes up position 1, and note that it starts counting from 1, not 0. Note that this numWords key here doesn't specify the number of words in the vocabulary. It tells us whether we capped the vocabulary. So if we had instantiated the Keras tokenizer with numWords equals 10,000, then the tokenizer would have kept only the 10,000 most frequent words. To see how large the tokenizer's vocabulary is, we can look at the number of entries in the word-to-index dictionary, and it shows we have almost 46,000 unique tokens. Okay, so at this point, we have trained a Keras tokenizer on our training data. The next step is to vectorize our training data. Here we're going to use a simple bag of words approach, and by simple I mean binary, count, or TF-IDF as we learned in part 1. An important note here, now that we understand how neural networks work, there are much better ways to vectorize our text, but since we haven't learned them yet, we're sticking with these simple approaches for now, and we'll see the shortcomings of that in this demo. The Keras tokenizer comes with a convenient method to do this called texts to matrix. By default, it creates a binary bag of words. We'll vectorize the first post in our training data as a demonstration. What we get back is a vector of length equal to the size of our vocabulary. And as we would expect with a binary bag of words, most of the values in the vector are 0. We can take a look at which indices of this vector are set to 1, indicating the respective token is present in the text. And we can retrieve the tokens using the index to word dictionary. Okay, so those are the tokens from the first post after pre-processing, and it's 1 token shorter than the original text because the word printer occurs twice in the original. In addition to binary, the text to matrix method also supports other modes, such as count and TF-IDF. So here we tokenize the first post using TF-IDF, and these are the relative scores of the present tokens. But we'll stick to a simple binary bag of words here. Feel free to experiment with other modes. Okay, so now we're going to vectorize the entire training set. There are about 9,600 documents and a large vocabulary of over 40,000 tokens. Now we know that once vectorized, the vast majority of the resulting matrix is going to be 0. So rather than holding a plain 2D matrix, we'll leverage TensorFlow's sparse tensor data structure to store them more efficiently, when we learned about sparse tensors in part 1. The good news is they work seamlessly with Keras, so we can do that by calling text to matrix on our training data and passing the result of that to a method which converts from a dense to a sparse data structure. Despite using a specialized data structure, we can still see the shape of the original matrix. Okay, so here our vectorized train set is about 9,600 rows, which represents the number of posts, and about 46,000 columns, which represents our vocabulary. We also need to vectorize our labels. Our labels are currently a single vector of integers. You may remember that when we do multi-class classification, we need to one-hot encode the labels. There's a way to avoid one-hot encoding, which we'll see later, but we'll stick with it for now. To one-hot encode our labels, we'll use a Keras utility called toCategorical, which does this for us, so we'll pass our labels to that utility. And what we get back are one-hot encodings. The shape is the number of documents by the number of labels, which is 20. And if we look at the one-hot encoding of the first label, the index corresponding to the label is set to 1, and the text label for that is Windows Miscellaneous. Next, we'll do the exact same thing with the validation data as well. Okay, so at this point, we've tokenized and vectorized our training and validation data. We're ready to build an initial model. Keras provides multiple ways to do this, but the most straightforward is the sequential API, where we can specify our model as a sequence of steps like an assembly line. So here we're calling sequential and passing it an array of layers. And there are all sorts of layers available out of the box ready to use. We'll use a variety of them in this course, and you can learn more about them through this link here. So here we're building a simple 3-layer model with 2 hidden layers of 128 units, both using relu as the activation function, and an output layer with 20 units and using softmax since we're doing multi-class classification. And our input will go into the first layer and the data will flow sequentially through the rest of the layers. Hopefully this API and style looks straightforward. Now one thing I'm doing here is making sure the weights initialize to the same value every time. I'm doing this by setting the TensorFlow random seed to 0, and in each layer, specifying a kernel initializer with a fixed seed as well. I'm doing this only so that you and I get the same results in this demo. If you want different weight initializations, just remove the setSeed call in the initializers. Once we've declared the desired architecture, we need to specify the other details we learned about in this module and compile the model. Here we're specifying the optimizer we want, in this case RMSProp, the loss function, categorical cross entropy, and the performance metric of interest. Since our data set is balanced, we can get away with accuracy here. Okay, we're ready to train. Similar to scikit-learn, that's as simple as calling the model's fit method. Here we're passing it the training data and labels, asking the model to train for 15 epochs, so to cycle through the entire dataset 15 times, a batch size of 128, and we're also passing in our validation data. This will make the model test itself on the validation data after every epoch and output how the model is doing, as we'll see now. Okay, so here we're getting a running report of the model in action along with the accuracy and loss on both the training and validation set. As you can see, the loss keeps decreasing and the accuracy keeps increasing on the training set, and for a while, the same thing happens on the validation set. But after a few epochs, performance on the validation set starts to degrade. Around epoch 5, the validation loss starts increasing and accuracy starts plateauing until it eventually starts decreasing as well, signaling the model is starting to overfit on the training data. Okay, so training is done. What we can do is plot the validation and accuracy on the training set versus the validation set. And to get a clear look at this, I'll open the graph in a new tab. Okay, so the top graph shows the training and validation loss over epochs. And we can see at epoch 4, the validation loss turns and starts increasing. Below that, we can see accuracy starting to plateau and not get any better around the same time as well. So our current model, at the end of 15 epochs, has overfit the data, and we know that validation loss was at the lowest at epoch 4. So what we'll do now is train a new model with the identical architecture, but this time for only 4 epochs. And the idea here is that we should then arrive at a model that's as accurate as it can be without overfitting, given the current setup and initialization. And once that's trained, we can see that validation loss kept decreasing till the end. And we can summarize our current model with the summary method. So here we see that the first layer has almost 6 million parameters, which seems rather absurd for a problem of this size, and significantly fewer parameters in subsequent layers. These layer names here are provided by Keras since we didn't explicitly assign names to our layers. If you're wondering how these numbers are calculated, let's take the first layer as an example. So our vocabulary currently is almost 46,000 tokens, which corresponds to the number of columns in our bag of words matrix. The number of units in the first layer is 128, so the number of parameters is equal to the vocabulary times the number of units plus the number of biases. Remember that each unit has a bias, so that's 128 biases, which leads to the number of params we see in the summary. So the reason why we have so many parameters in the first layer is because our input vector is large, and we'll have more to say about that later. We can also look at a layer's weights. Here, we're looking at the weights of the first layer. The first collection is the unit weights, and the second collection are the biases. We can drill down on that as well. Here, we're looking at the weights from the first layer's first unit, which is 128 scalars. What do these numbers mean? I have no idea, and this difficulty with interpretability is part of the drawbacks of working with neural networks in general, but it's actively researched, and we'll see later that some neural network-based models do offer some interpretability. Okay, let's try this model on our test set. We'll fetch the 20 newsgroups test set and make sure we don't include metadata. And pre-process the test posts in the same way. I'll fast forward through this. Once we have our pre-processed text, we'll vectorize both it and the labels. That'll take a short moment. To run our model on the test set, we'll call its evaluate method and pass it our test inputs and targets. Evaluate returns a 2-element array. The first element is the loss, and the second element is the accuracy. Random guessing would result in an accuracy of 5%, so this is definitely better than that, but it still falls slightly short of our naive Bayes model. Let's take a look at a confusion matrix like we did when we were building the naive Bayes classifier. To do that, we need to generate predictions, which we'll do by calling the model's predict method and passing it our test inputs. Now, the predict method returns whatever comes out of the model's output layer. Since we're using a softmax on the output, it returns a bunch of 20-element arrays. Here we're looking at the output for the first test post. To turn that into a prediction, we need to find the element in the array with the highest value and take its index. That index then corresponds to the category the model is most confident in this case 8, which corresponds to motorcycles. Alright, so the first post in the test dataset was classified under the motorcycles topic. Okay, so here we'll plot our confusion matrix. This time we won't normalize, but rather just show the raw number predictions, and I'll open this in a new tab. The patterns we see here are similar to what we saw when we used naive Bayes. There's a relatively brighter cluster on the upper left where the technical topics such as PC hardware and Mac hardware are confused for each other, and on the lower right where religion, guns, Christianity, and politics overlap and get confused for each other. A lot of atheism also gets misclassified as Christianity or general religion. What we're also seeing here is a high number of correct predictions for motorcycles, but a lot of other topics are also being misclassified for motorcycles. There is a slightly brighter vertical strip here. If you initialized your weights differently by removing set seed and the kernel initializers, then you might see something different. Let's take a look at the classification report to get a better idea. Okay, so specialist topics such as medicine and hockey and cryptography get good scores, while atheism, religion, and politics are always hopeless. Motorcycles in particular has decent recall but mediocre precision. It looks like when the model isn't sure, it's biased towards motorcycles. Let's investigate this category a bit more. I'm going to copy and paste the rec.motorcycles label here to get the category index. So that's category 8. First, we'll get the classifications for this category of interest. So these are the indices of posts which the model classified under the motorcycles category. So post 0, post 2, and so on. Next, we'll get the indices of incorrect classifications. So these are the indices of posts which the model misclassified. Finally, we'll get the indices of posts which the model classified under motorcycles but was wrong. And there they are. So these posts were all misclassified under motorcycles, and it looks like there were quite a few of them. And this matches with what we saw in the confusion matrix and classification report. We'll use this simple utility function here, which takes a post index and prints the model's classification for that post, the actual label, and the post content. And we'll look at the top 10 posts which were misclassified under motorcycles. Okay, so right away we can see some ambiguity here. A handful of posts after pre-processing turn out to have only a handful of words or are just blank, like the second one here, which only has the words word and yes, which basically can't be classified. We should get rid of them. A few of these posts are ambiguous or confusing because they're lacking context. Okay, so let's make another attempt. We'll use this simple function here to filter out posts under a certain length, and we'll filter our training corpus. Here we're setting a minimum requirement of 5 tokens to be included, and if the post doesn't meet that requirement, we remove it along with its label. Okay, so that took away a few hundred posts. We'll do the same with the testing set. Now, of course, this also means we should do this at inference time and have policies in place for posts which don't meet this requirement, but that's not a concern at the moment. Since we filtered our training set, we'll redo the train validation split, and we'll revectorize the train validation and test sets. Okay, so for our next model, we'll try a few things. First, we'll add an additional layer of 128 units, and on the last hidden layer, we'll add a dropout of 30% to hopefully make the model more robust and less likely to learn accidental relationships, which I imagine is more common with bag of words models. All 3 hidden layers will have their weights initialized with He initialization, and once again, I'm fixing the seeds so that we get the same results. And lastly, we'll use early stopping. That is, we'll have the model monitor the validation loss, and if it stops improving, training will halt. This will save us the trouble of training another model with fewer epochs like we did earlier. For the early stopping, we're setting this patient parameter to 1. Patience means how many epochs to go without an improvement before stopping. Since we saw in our graphs earlier that the validation diverges pretty quickly, we're setting it to 1. If you see in your graph your validation tends to plateau for a bit before improving again, you can try a higher value. And in the model.fit call here, we'll pass the early stopping directive as a callback. The epochs and batch size remain the same. Okay, we'll let that run. Alright, so it looks like it stopped at the end of the third epoch, and as you can see, it kept improving to the end. Okay, let's try evaluating on the test set. Okay, the accuracy went up a bit, and we're basically now on par with the naive Bayes classifier. If we look at the confusion matrix, we don't have any bright vertical strip under motorcycles, or anywhere else for that matter. But still, the weak areas around the upper left, lower right, atheism, and electronics remains. These are the same gaps we had with the naive Bayes classifier. Looking at the classification report, the F1 scores around the more specific topics remain good. The F1 score for motorcycles is also now good given the nature of the data, while the topics with a lot of overlap remain poor. Let's try some inference. This is a simple method which takes in some raw text, tokenizes it, vectorizes it, runs the model's predict method on the vector, and returns the category along with the probability. Once again, I found some posts from Reddit, and these may or may not classify correctly depending on how the neural network turned out. So the first post is okay with 99% probability, second post is good, third post is good, and so is the fourth post. Okay, so that was a demo of tokenization, vectorization with simple bag of words, building, training, and improving a neural network, and using it for predictions. We won't bother improving this any further, but if you want to try a few different things, you can try different bag of words modes like TF-IDF, filter out words based on low and high frequency, train with more data. For example, you can scrape posts from similar subreddits, use another optimizer, experiment with deeper or wider layers, and play around with the regularization. But to be honest, I don't think there's much improvement to be had here because in this case, the bottleneck is the data. First, a lot of categories overlap with each other as we saw with a few technical, political, and religious topics, and those drag the overall scores down. If we stuck to only the specific domains, our accuracy would shoot up. There are also a lot of ambiguous posts which, taken alone without context, even a human wouldn't be able to classify correctly. Using simple bag of words vectorization on top of ambiguous posts makes it harder because we lose any sense of order. And our input is huge and sparse with little information value, which we're then forcing into a very narrow model of 128 units at the first layer. If we set the first layer to have 20,000 units, so roughly half the size of our vocabulary, we would end up with hundreds of millions of parameters, which is absurd considering state-of-the-art models of those sizes can accomplish much, much more. So beyond applying what we learned and showing the basics of Keras, I hope this also demonstrates that data quality and vectorization techniques have huge impacts on downstream modeling performance. If the first two aren't up to par, throwing more layers at the problem won't go anywhere. In the rest of the course, we're going to learn superior techniques to vectorize text for neural networks, techniques which lead to vectors packing a lot more information. Until then, if you're interested in learning more about TensorFlow and how to use its low-level features to build a model, then here are a few informative links to work through. Learning the low-level features can help you build custom models and have greater control over the information flow. I've also included links to learn more about PyTorch as well. There's also a classification exercise here using a TensorFlow dataset of Reuters news articles. Okay, so that was a lot of information, and if you're new to this, there's no expectation that you remembered all that. The only way to build an intuition for this stuff is to experiment with it in different scenarios and see what works. Alright, after 2 intense videos on neural networks, we can define deep learning. And in terms of a structural definition, a deep neural network is just anything with 2 or more hidden layers. That's it. Geoffrey Hinton, one of the pioneers of deep learning who toiled away on neural networks even when they were unfashionable, had to rebrand them to get past conference gatekeepers once he or his colleagues made a breakthrough. And so, if you know how neural networks work, you know how deep learning works. Conceptually, deep networks are about learning representations. In the previous module, we talked about how neural networks are just functions which map inputs to outputs. They learn an approximate function through a trial, error, and adjustment process. It's ultimately the same with deep learning, but with multiple hidden layers, where we can view each layer as learning a representation of the layer preceding it, a representation that serves the goal. Consider images, for example. Imagine if we had to manually extract features to tell objects apart in an image. How would we manually extract features to help tell cats apart from dogs? It's untenable. But with deep learning, we ask the framework to learn how to take an image input and turn that into some classification output. The layers in between then learn complex aggregate representations such as how to discern lines in different orientations, all the way to features such as eyes or wheels. The network learns useful features for us, and we can take these layers and leverage them for other tasks in a process called transfer learning, which helps us avoid repeated work and allows us to use large models without having to train them ourselves. And we will see how to do that later in the course. Just note that with NLP in particular, data wrangling is still a big deal. Text is messy and noisy, and since language is constantly changing, there's more work involved in setting up a good pre-processing pipeline. To end this module, here's a list of defaults you can use when training a neural network model from scratch. ReLU for hidden layer activations, He initialization for weights, maybe use batch norm if you're doing something other than NLP, leverage dropout and early stopping for regularization, and Adam or RMSProp for the optimizer. Since RMSProp is adaptive, a learning schedule isn't necessary, but if you use one, that'll control the range of scaling and may help with convergence. Alright, so that concludes our 2-part deep dive into neural networks. In the next module, we'll focus back on NLP and learn how to encode the meaning of words in our vectors.